Hello, everyone. Thank you for introduction. I'm Hiroshi Iinaga from OKI Circuit Technology. Today, I'd like to talk about this topic. First, let me briefly introduce our company. OKI Circuit Technology, as you can see on this slide, our main business is developing, designing, and manufacturing high-layer, high-speed, and high-density printed circuit board. Recently, we have developed high-layer PCB up to 124 layers, especially for AI semiconductor test devices. So next, for high density, we have technology for an aspect ratio of 24 for fine through holes. We have also developed technology for 0.23 pitches through hole using 8-micron drills and plating for 3D thickness board. Next slide, so this is door diameter 0.08 millimeters. So this drawing is so length is not enough for 3 mm ball thickness. We drawing is double access to, and then we are reaching up to 0.23 millimeters for fine board. So this is our so this is our technology. PCB are used in a wide range of fields, mainly for industry applications. So, first is semiconductor testing. Second is defense in aerospace, telecommunication broadcoming, and measurement equipment, public infrastructure, and so on, so medical. Today, from the viewpoint of PCB manufacturers, I'll focus on high-speed transmission technology, which is becoming more and more important. I'll give you an overview of today's presentation. I will explain why such high speed are needed based on the market trends driven by AI and data centers. And I'll explain how these demands affect printed circuit boards. I'll talk about 3 key technologies: materials, resin and glass cloth, processes, surface treatment, and backdrawing, and design via impedance and via structure, including the latest trend. So this graph shows data traffic in Japan. This data is mainly from ISP. ISP is the internet service provider and does not include traffic inside data centers. As you can see, data traffic has significantly increased, especially since 4G became common. So, and after the COVID-19 pandemic, around 2020, it has been growing by 20% to 30% per year. This main reasons are the more video and imaging streaming and also internet and an increase in remote work. This trend is similar worldwide. For the past 10 years, data traffic has been growing by more than 20% annually. So every year, 20% up, that means 4 years before market ready for it. So which are account for the largest portion of this increase in data center traffic? Please look at the next graph. So there is the traffic, telecommunication, and enterprise and data center. Now currently, so the largest traffic volume is especially in the data center. So especially connected to the network and the AI server between data center, handling the huge amount of data at high speed, driven by the recent AI boom. So this is learning the volume of the AI, especially since arrival at the generative AI like ChatGPT. So the amount of learning data in data center has exploded. Reportedly increased by about 100 times in the past 2 years. On the other hand, Semiconductor and memory are evolving with more data, but transfer speed is often lag processing. Standards like HBM3 and HBM4 and PCIe 6 and 7 helps bridge this gap. This gap means to catch up the running volume of AI, they build many data centers. But many data centers electric need, and data center become a big heater, needed water for cooling. So low power and efficiency data transmission required. Thus, more speed needed. So this graph shows data center power consumption report, focus report. So 2026, so maximum size is consumption 1,000 kilowatt per hour. That means Japan same power of consumption. So now now you understand. So air density consumption electricity is a big issue. We must reduce this power consumption. That's why high speed needed. So this is the internet speed roadmap for networking. So data center network capacity doubles rapidly every 2 years. Internet speed about this graph shows about 6 years doubling. Not enough, but now it's 1.6 terabyte is running. And so some internet network is and everything to cover is already on the network. So this standard is subsidized in applications. So this graph shows from same and for my curriculum. So you can see that this is a huge AI now because an AI data center need more data, need more data consumption. This is the top of the mountain. But next is this is provider and service provider and automotive and 5G automotive and enterprise consumers. So this is survived post reason because huge AIs need more money, high speed needed. But this is not enough. So standard subdivides. So we must think about some proposals, good solution for this each standard. So data takes many routes from AI processing to our homes. Even if data center are fast, user experience won't improve if other parts of the network can't keep up. Therefore, identifying and fixing these bottlenecks of the network is important. This is another view of network. If data center speed up, but not network still same for subscriber, not get improvement. Therefore, we must improve it. All network speed up. So to eliminate this bottleneck process, from now, I introduce three points. First, this is bottleneck is submarine cable. This diagram shows from the planning and from Japan to West Coast, submarine optical fiber cables. Now, 1, 2, 3, 4, 5, 6 big projects is going. So, but you can see the main. So you can see the main blue, meta, blue. So they understand bottleneck between Japan and West area. So they must eliminate for business. So next is LSI. An example effort to solve this bottleneck. So LSI, the evolution. This graph shows the switching capacity trend of LSI for routers. This is graph shows the switching capacity trend of LSI for routers for protocol. So performance and doubling accumulates every 2 years. So they understand this networking rule. So LSA capable processing large capacity size like that. Now it's 51.2 terabit an hour. Their use is now is maybe 5 nanometer LSA technology. That means their use is one generation behind newest LSA technology. So now AMD and TSMC Apple using 3 nano, I guess. So next generation, since few years after, they use the 3 nanometer. Then this volume is 100 terabits per second. So now we explain bottleneck of optical fiber. Optical fiber evolution. In the past, optical fibers achieved large capacities. However, there is a physical limit to the amount of information that can be transmitted through single fiber. Therefore, similar to LSI, transmission capacity being improved through technology innovation, multi-core technology. Now, high capacity transmission is there are 1.7 petabit per SO. So, what kind of transmission speed are required in this situation for printed circuit board? So, this is also roadmap of Ethernet. Currently, 1.6 terabit per second Ethernet is under discussion as specified standard. In this case, a transmission speed is 224 gigabit per lane is expected. And the flexion usage will be around 56 gigahertz because they're using powerful technology. So if we consider next 3.0 terabit per second beyond that, simply calculated suggested 400 gigabit per lane. However, with current technology, it is considered very difficult to stable transmission because the frequency is 100 gigahertz using the palm core. So, very difficult. So, it is still unclear whether it's next generation and so palm 6, yes, palm 6 is 75 gigahertz, or there will shift to the optical technology without going through PCB. Now, this point we're talking about frequency is 50 gigahertz, 56 gigahertz. There are 3 main technologies for trying to overcome the material technology, process technology, and design technology. Using better material processing and optimized design improves performance, but involves a cost trade-offs. So balancing performance and cost for material process and design technology is key today. I'll explain these 2 technologies because it's using the good material, good process, as positive, not effective. So we are using a newest technology, we use best material and best solution. As next is, for example, for subscriber or sometimes internet service provider, we need a newest technology. So we supply customer requirement of best performance, and best pricing process. Okay, next thing is material. So first, let's talk about technology. So now we're talking about 204 Gbps, 65 gigahertz. So the mainly material requirement in case 3.0, 0.001, and less at 10 gigahertz. So now you can see this graph. So like this is now it's not so exists 0.001 material. So goal of 0.0 they are developing next maybe Meg 8 equivalent. Likely Meg 9. PC materials mainly consist of resin, glass cloth, and copper foil. Here I'll focus on resin and glass cloth and introduced effort to reduce their loss as well as latest trends from the material manufacturers. So, materials is now important tangent loss. Why tangent loss? To reduce high frequency signal, we focus on two main types, conductor loss and dielectric loss. Conductor loss, this comes from the conductor resistance and the skin effect. Copper is low resistance. But if we need furthermore in silver, skin effect currently concentrate on surface, even with copper. We need further loss reduction. So bus conductor losses, so now it's limited because we need silver is very expensive. So dielectric loss, it measured by dielectric constant and dielectric tangent, which is important. This quotation shows a lower dielectric constant helps reduce loss. Impact is limited, just root. However, the dielectric loss tangent directly affect loss. So reduced tangent delta is more effective. To achieve loss tangent, we focus on three key material properties. First, non-polar materials. We aim to reduce polarization. Less polarization means less energy loss when dipoles vibrate in high frequency field. Second, symmetric molecular structure. Symmetric molecular structure respond less to high frequencies, which reduce loss. For instance, water is an asymmetric structure and has poor high polarization properties. Because of the if you're using microwave, water is easy change to heat by microwaves. So asymmetric like this and symmetric and unsymmetric molecular structure is not best way, not worst way. So third, and making molecular change longer to improve crystallinity makes the material structure more rigid. Your big molecular size, not so easy to move. So that means so we used many materials, glass cloth and resin, and to reduce the loss using this point. Okay, high dielectric. Good example for three approaches is diamond. Unlike conductive graphite is conductive, but diamond is insulated. So diamond carbon atoms same. So button in the diamond strong because it's a now insulating crystal structure. This is so changes the orbital change, sp3 orbital. So and relativity high dielectric constant about 5.6, but it's a highly symmetric crystal structure results in very low dielectric loss tangent of 0.004. Very low dielectric loss. And this same concept applies to reducing range loss in resin and glass crosses. So next generation properties, I think the need for both resin and glass crosses, low dielectric loss is needed. So this graph shows optimizing dielectric loss tangent by controlling resin and glass cross. Since PCB material is composite of resin and glass cross, so its dielectric loss tangent can be approximately determined by the volume ratio of the two. So this graph shows how the overall dielectric loss tangent changes when the resin content varies. Here we assume very low dielectric loss tangent, 0.05 for the resin itself. So case 1, blue line, when the dielectric loss tangent of glass is 0.028. So equivalent to common is the NE glass. Case 2 is so underline when using the next generation glass cross with dielectric loss tangent 0.01, maybe a little NZ glass. In PC manufacturing, the resin content of represents generally using the range of 50 to 60% for dimensional stability and process ability. Looking at on the graph in this range, case 1, if the resin content is around 60% to 70%, the overall dielectric loss tangent about 0.0013 to 0.0014. This is equivalent neutron side. But we must improve. Case 2. Using next generation glass cross tangent 0.0011 with a resin content of around 6%, the overall direct loss tangent can be potentially by reducing around 0.007 to 0.008. This level can achieve the target ultra loss property. So, next I will introduce the latest effort representing material manufacturers. So, die-cell mid-turbo pillar. So, die-cell corporation. Die-cell is developing ultra-loss materials using different approach from conventional resin system by applying and modification and cross-linking technology. They are aiming for the dielectric loss technology below 0.001. Particularly, good point is the result itself has flame resistance. Generally, PPE-based materials have an issue of low flame resistance. And flame retardant like bromine compound are often added. However, this can affect electrical properties and processability. Die-cell materials have excellent flame resistance in the resin. This offers significant advantage in reducing the risk of properties. And very low dielectric loss tangent of 0.00094 at 10 years has been reported. So, this is the usual dielectric resin loss, and so this is the olefin, but die-cell is also very small. And so next, I'll try to do some video.
Video?
Okay. No comment, this is for fun now. This is so. Memory. Try again. That means equivalent to U95.0. So this is the cross-section view of the PP-based material. You can see that. So this is glass, and this is you can see silicon clear, and this is the flame retardant. You can see the many flame retardant. So this is not good for properties next generations material. To reduce flame retardant is important. So next, Nitobo. Nitobo glass cross is a leading market maker of low-loss glass cross with products like an NE glass and NER glass. The newer NEZ glass often even better properties with an extremely low direct loss tangent around 0.001. Combining such high-performance glass cross with the ultra-loss resin can help achieve total PCB loss tangent near the below 0.01. So they also have a roadmap for next generation product DX2. DX2 is maybe I think it's the same as property of the Q glass. So this is, I think DX2 is the ultimate glass cross, I guess. Next, Pillar has been developed and manufacturing low direct loss materials based on PTFE, known as TEPA. For many years, PTFE originally has excellent electrical properties, low direct conductance and low loss tangent. We hear that Pillar is aiming to develop materials with direct loss tangent below 0.001 by 2025 this year. So Pillar is developing technology to overcome this, such as making them thinner, because so thinner material use required. So furthermore, their roadmap includes the development of next generation materials called beyond PTFE, which aim to surpass the properties of PTFE. This is likely target and flexion band about 100 GHz, or even the terahertz range like 300 GHz, anticipate for future 6G communications. The next is process. So when the high frequency signal goes through the conductor, the current went to concentrate near the surface of the conductor. This phenomenon is called the skin effect. The depth to which current flows becomes shallow as the frequency increases. Above 20 GHz, skin depth becomes shallow and a few micrometers or less. At 50 GHz, which is central to today's discussion, is about 0.3 micrometers. And at 100 GHz, it reaches about 0.0 micrometers. That means, and so in case of surface roughness, skin health effect, so, very sorry. And so in case of the 50 GHz, 0.3 meters or something, in case of the 100, 0.22, not so change. But so in case of 20 GHz, so this is very shallow. So this graph, so surface treatment outer layer is important. This graph provides the JPC compares the SEH characteristics for various plating treatment. Electronickel immersion gold ENIG, electroless palladium immersion gold EMPIG, and direct gold zinc and 6 is PIG. So the result shows ENIG which contains nickel layer. So with a high electric resistance, tend to have a great loss confinement compared to direct gold plating, especially in high frequency region, where the skin depth is shallow. The presence of thickness of the nickel layer have significant impact in ERPG, which surpass the influence of the nickel layer. Shows properties close to direct gold plane up to about 50 GHz. However, at high frequency, like 100 GHz, the difference due to the absence of nickel layer becomes clear, which can be explained by the skin effect. So inner layer treatment. So inner layer treatment, which ensures adhesion, also affects transmission loss. Using Meltron 6 materials, we see a clear difference between conventional etching and chemical bonding processes, especially 50 GHz. Etching treatment creates a rough copper surface for physical adhesion. However, this roughness increases signal loss at high frequency. Chemical bonding treatment responds to a chemical bond for adhesion. It keeps the copper surface smoother, which helps reduce transmission loss because it doesn't. It's a copper surface. It also better maintains the conductor the original shape. Furthermore, because chemical bonding does not etch the copper, it makes this lead to the difference in DC resistance. It is so same pattern and same difference, so etching process and chemical bonding. In this case, resistance is 50% different. It is so good for DC resistance. Next, so process backdooring. Stubs on through vias can cause a resonance in the transmission path of high frequency signals. We use TDR to check the remaining stub length after backdooring. TDR can detect impedance mismatching and resonance point if stub remains. This allows us to verify our process chain quality. If a stub is present, impedance will fluctuate significantly, at certain fractions appears as a resonance point. But this is so this graph upscaling. So this is so back after backdooring. No remain bar. But this is so we can see this. You can see the bar. This is so remains backdooring bar. So TDR method easily to find and checking this find. This graph shows the length of the backdooring stub affect electric characteristics. No backdooring. This first resonance occurs around 12 GHz. And the second resonance is seen at 34 GHz. With backdooring, the resonance point at 12 GHz has disappeared. But new resonance point appears at higher frequency in this 30 GHz. You can see this. Secondly, this resonance frequency, its attenuation depends on the remaining stub lengths. So this is so different stub lengths. So high frequency regions like 50 GHz and above, managing the remaining stub lengths to be extremely short, maybe below 150 megahertz is essential for good transmission. So I pattern. Let's look up how much material and process technology improvements discussed so far contribute to the actual signal transmission quality using the I-pattern evolution. This result shows the simulation results. Also, based on the S parameter or some material properties, we measured at input this parameter to simulation. So one is a conventional process, melton 6 materials and conventional etching process. Middle 3 includes melton 6 material plus chemical bond process. Number 6 is the latest material, melton 8 plus chemical bond. With number 1, with conventional material and processing, the eye opening is not so small. Middle, using the same melton 6 material simply changes the inner layer treatment to chemical bonding, really improves eye opening. Number 6, by combining even high performance melton 8 and so chemical bonding, very clean and large eye opening is obtained. Demonstrate significant improvement in the ability to handle high-speed transmission. Thus, just by changing the inner layer treatment to chemical bonding, a characteristic impedance effect improvement effect equivalent to 1 lakh upgrade material. That's very important. Next. So, design via construction. Finally, I'll explain design technology, especially via structure optimization and impedance control optimized via structure is very important for high frequency characteristics. This graph compares high frequency characteristics in such a loss. When just this is number 1 4-run diameter. So when the beer diameter is made smaller versus conventional diameter, by making the beer run diameter smaller, impedance mismatch in high frequency region is suppressed, and unwanted reflection and resonance are reduced. As a result, thus, this appears an improvement in transmission loss in high frequency region. So next, beer structure. Backdrawing is very effective for eliminating stub effect. Also, microbears from build-up also effective. But so many, sometimes many stub build-up layer tend to appear resonance, return of resonance. So, in this case, so before design, it's a case by case. So before design we simulated and which is via construction effective in this customized requirement. So in this case, simulation is very important. Next page, I'll explain via impedance. So number 3 via impedance. Next page, I'll explain. So in high-speed transmission, control via impedance itself is extremely important. Not just matching transmission line, traditional method. Traditional method like placing ground via, however, about 50 GHz controlling the via impedance is very essential. The impedance of via is determined by inductive M and capacitance C. This main design parameter are below. This is parameter to control impedance. Many parameters needed. So this is total both thickness of each layer, diagonal diameter, diagram diameter, antipath diameter. Antipath diameter of the diameter of the clearance area around the via, and via placement or alignment. So inner layer alignment accuracy, sublengths, and consider the process deviation. While optimize these parameters one by one, it is also necessary to consider manufacturing variation that can occur in the actual production process, such as misalignment between the layer of misalignment of the deformation position. These variations mainly affect the capacitance component of the peer, leading to impedance fluctuation. In simulation, it is important to secure design margin that can achieve the target characteristics even concerning these variation factors. We optimize these parameters using simulation tools and then repeat prototyping and actual measurement to achieve the target impedance characteristic. So this is the result of optimizing via impedance control on board with thickness of 6.3 meters, 15 layers using Vector 6. First, the simulation results. So with actual measurement, result and simulation of the very similar, you can see that they match very well up to the about 60 GHz. This is the result of the precisely optimizing the via diameter and antipath diameter, stub lengths with the backdoing, and so on, as mentioned earlier. This is an example showing how important optimization by design, not just material. The graph is towards lower of this area. The TDR measurement result of the optimized via structure, it can be found that impedance variation in the via section is very small. Staying with the extremely good ranges, for example, plus minus 0 relatively to the target abuse. This is also due to the optimized design. Now we can see this is graph is so blue line left blue line is maybe on the background and red line is build up. So you can see that this last graph is so via impedance control. You can see so in high frequency control via impedance important. Summary. Accelerating data mine for high speed is the evolution of AI and data centers. The demand for high-speed transmission in the circuit board is ever increasing. Coordination, material process, and design to support high-frequency vision exceeding 50 GHz. It is essential to collaboratively advance three-element low-loss materials technology, precise process, and so via technology. So implement via impedance control. In particular, accurate impedance control of the via section is key to achieve the high-speed transmission. Number 4, realize of the 50 GHz band transmission by combining these technologies. Stable signal transmission in the 50 GHz band is becoming the reality. Number 5, challenging the next generation, achieving the transmission into 100 GHz range, and beyond the further breakthroughs are required in the aspect of material process and design. We will continue to work on these important challenges for the next generation. Thank you very much for your time and attention.
Thank you very much, Iinaga-san. It's a really interesting topic. So, any questions?
Iinaga-san,
Right.
HEP is working on a surface treatment project up to 110 gigawatts. What else would you suggest that this group do to address the next generation for 100 gigahertz and 1.6 terabit per second networks?
It's like that.
Just the experience you give here.
Surface treatment is so still important. So to reduce the resistance on the surface. And so now but contact in the conductive loss and copper is a very, very, very low resistance. As I told, next to silver. But silver is not good for not good for cost and migration. But in case of the high frequency cable, like they say, they use it surface coating is silver. So I think that this is so next challenge. I think.
May I ask a follow-up question? So beyond the surface treatment for the surface, you talked about the inner layer treatment. How about things like via structures? Do you see when we get to 100 gigahertz, let's say for the optical networks, get to 1.6 terabit per second, or the next generation 6G wireless that they're talking about, sub-terahertz spectrum for 6G? Do you see multi-layer structures with vias affecting that? And to what extent are they going to be able to run these very high speeds in very complex printed circuit boards?
So via construction is a very difficult question still. We talk about so many times of via structure checking and simulation about 10 years ago. So maybe transmission on the line is simple. But via structures, you may sometimes the backdooring, sometimes many times also micro via, sometimes so this combined. So as I said, that means via construction control is a key point for 100 gigahertz for future high-speed PW technology.
Thank you.
Any questions? Any questions from online?
Shinichi,
Yes.
could the speaker explain the difference between dig 1, dig 2, and dig 3? I believe it was in slide 35 or,
What was
36.
36 pages?
yeah.
So difference between dig 3 and dig 2 and dig
Yeah,
1.
what is the difference between dig 1, dig 2, and dig 3?
I'll explain. And so maybe which speaker made a mistake besides time before. And so difference is so VIG1, VIG2, VIG3. So this is so thickness of the so AU and roughness of the so rest of so copper. So because so now we're talking about so dips of the skin effect. So in case of the 100 units, maybe 0.21 micrometer is a so skin dips effect. So in case AU gold is 0.0 is very, very thin, but so 0 and fast. So in this case, it's an effect of the bottom copper roughness. Difference is important. That's okay.
Yeah, thank you. Thank you.
And I think Rich and I are very interested in the ratio of conductor loss between smooth DIG2 and rough DIG3, thick DIG. So can you estimate the ratio of conductor loss between copper and gold on those surface finishes?
Yeah, thank you.
So, do you need help? I need your help.
Let's go to the microphone.
I help?
Yes.
So that's on the real corporate. The difference that dig 1 and dig 2 is the roughness of the copper underneath the gold. And the dig 1 and the dig 3 different thickness of the gold. And we understand the skin effect depth at the medium area is around 0.4 micrometer roughly. So that's why the test is a target to see the difference in loss, tolerance.
I think there may be a sweet spot between big 2 and big 3. Any questions from Rich?
I'm not sure that I got everything that was said. Are we kind of saying that the thicker the gold, the smoother the surface, and therefore the better, the less insertion loss? Are we saying that that conductive layer is now smoother and that may contribute? Is that?
Because gold thickness is very effective. More than
One more.
hello, can you hear me?
Yes.
Yeah, I'm Mr. Toda, Medical Electronics. Actually, we make in JPC, work this effort and published this technical report this year. And your interest is the difference between dig 1 to 3, comparing dig 3 to dig 1 is dig 3 has thicker gold thickness,
Right.
0.5 micron versus 0.05 ton, and comparing dig 2 to dig 1 is surface roughness.
Yeah. Okay.
After circuit, after fabricating circuit, the roughness of the top couple is very smooth in dig 2. Also, gold plating surface as well, and roughly the difference of S21 between dig 3 and dig 1 is can we show the graph here 0.1 about 0.1 at 1 gigahertz, and by 10 millimeter line length. And the difference between dig 2 and dig 1, that means surface caused by surface roughness is only 10%, less than 10% of 0.1 as S21. So the point is the thicker gold plating thickness is very effective, more than surface roughness. Is it the answer for you?
Well, I think the explanation is very good. I mean, the good news is that in the testing that we have planned, I think we have this covered because
Okay.
we were smart enough to go with these thicker deposits. So
I'm sure what's going on in your side.
Yeah.
However, the surface roughness and plating thickness would be the issue, a key issue in your project, I guess.
okay,
Okay,
that's
thanks.
very helpful. Thank you.
Thank you. Any other questions?
So thank you for your good presentation and introduction of our PTFE material. So we would like to hear about the requirement for the CCL material after the 100 GHz. So that means, for example, it will be required less than DF, less than 0.001, or DK is under 2.8 or something. Like we'd like to hear your opinion.
Okay. I just waiting to the Hirasan's beyond PTFE.
Okay.
I think that this material, I think that under the 0.01, I think that so it's a killer material for the high-speed transmission laminate. Because it's now it's market, we're talking about 15 GHz and transmission. But as customer market requirement, maybe more. Because as now it's a very high frequency, it's a move to optical, but it takes a time. So maybe I think the 75 GHz, I think you are beyond PTP is a requirement for the market.
Thank you very much.
Thank you. Any other questions? If not, many thanks again to Iinaga-san.